There are 9 possibilities in the intersection of planes, outlined by 9 different cases. There are 3 possible ways for 2 planes to intersect, shown in cases 1, 2, and 3. There are 3 ways 3 planes can intersect, shown in 4, 5, and 6. If 3 planes have 1 or more solutions, that means that it is consistent. There are 3 possibilities for a system of 3 planes with no solution, shown in cases 7, 8, and 9. If a system with 3 planes has no solutions, it is considered inconsistent. The type of case can be determined by the normal of the plane. The first case we will discuss is case number 1. This is the intersection of 2 planes where there is an infinite amount of solutions and all the solutions form on one line. We will work on finding out what that line of the intersection of the 2 planes is. As discussed before, the first case we're going to be working on is the intersection of 2 planes, and we're going to be looking for the line which passes through both. So the equations we have here is A and B. Equation A is 3x plus 2y plus 5z equals 4, and equation B is 4x minus 3y plus z equals negative 1. So we want to find the line that intersects both equation A and B. So the first thing we want to do is method of elimination. So we multiply equation A by a factor of 4 to get 12x plus 8y plus 20z equals 16, and equation B by a factor of 3, which gets us 12x minus 9y plus 3z equals negative 3. The resultant of this is 17y plus 17z equals 19. What you want to do is then isolate for y. So how you do this is by bringing it to the other side and solving. So you get y equals 19 over 17 minus z. And now you want to do the exact same thing where you go back to one of these 2 equations. And I chose 3x plus 2y plus 5z equals 4 for simplicity. And then what I did is for y, I subbed in 19 over 17 minus z. And when I solved for it, and then what I did was I expanded and brought everything over to one side and isolated for x, resulting in negative z plus 10 over 17. And as we know that z is also always going to equal z. And for simplicity reasons, what I did is I changed every z into the letter t to make my final line of the equation a lot simpler. So 19 over 17 becomes, minus z becomes 19 over 17 minus t. And negative z plus 10 over 17 becomes negative t plus 10 over 17, and z equals t. So what you want to do is you want to find a point on this line, and how you do that is by substituting 0 in for all the t's, and I get this point right over here. And what you want to do later is add t times all the scalar multiples of t. So that would be negative 1, and 1. So the x is negative 1, y negative 1, and the z being negative 1. And this is your equation of the line that passes through both planes. Now that we have learned the intersection of 2 planes, finding the line, we no longer have to work on case 1 because we know how to solve it. Now moving forward to case number 2. In case number 2, the planes are coincident. Therefore, that means that there are an infinite number of solutions because the 2 planes are the exact same and they lie on top of one another.
Next, we'll be looking at case 2, which is the intersection of 2 planes, more specifically when the 2 planes are coincident. Coincident means when there's an infinite number of solutions and the planes lie right on top of each other. Looking at this question, determine if the planes are coincident. We have plane 1, which is modeled by 3x plus y plus 2z equals 5, and plane 2, which is modeled by 6x plus 2y plus 4z equals 10. What we can do first is we can analyze the normals here. Normal 1 equals 3, 1, and 2, and normal 2 equals 6, 2, and 4. Just looking at this, we can see that it is a scalar multiple of 2. What we can also do then is analyze the constants. Looking at d1, it equals 5, and looking at d2, it equals 10. We can also determine that it is a scalar multiple of 2. Since both the normals and the constants are a scalar multiple of 2, it can easily be determined that the planes are coincident. But what we can also do to further prove it is use substitution and elimination. So first we take plane 1 and plane 2, and then what we can do there is multiply plane 1 by 2 and then use elimination. When we do that, the 6's will cancel out, the y's will cancel out, the z's will cancel out, and the constants will also cancel out. What we'll be left with is 0 equals 0, which also means the planes are coincident.
Alright, now having finished cases number 1 and 2, we move on to the last of the 2 plane intersections, which is case number 3. Case number 3 is when the 2 planes are parallel, but they're distinct from one another, which means that there is a space in between and they don't intersect at all. For this case, there's not going to be a solution.
So next we would be looking at case 3, which is planes that are parallel and distinct. As you can see, the image shows that there are two parallel planes that are distinct, and you can see this by the space that's in between that represents that these planes will never intersect. So now I'll be showing you an example of how the two planes are parallel and distinct. So in this example, we will determine if the planes are parallel. So with the first plane and the second plane, first what we're going to do is we're going to find the normals. So the normal for the first plane is 2, -3, 4, and the normal for the second plane is 4, -6, 8. Now you can see that these two are scalar multiples by each other, because if you multiply the first normal by 2, you get the second normal. So knowing that these two normals are parallel, we know that the two planes are parallel. Now the second step will be to prove it. So to prove it, we're going to do substitution or elimination. So in this case, we have all our planes written out, and now we'll use elimination. So first, we'll just multiply the first equation by 2 so that both equations are equal, and we can start eliminating variables. So the next step, we're going to subtract. And after subtracting, what we're going to end up with is 0 is equal to -4. This shows that there are no solutions to these two planes, and that these two planes are distinct because these two constants do not equal one another.
Having finished intersection of two planes, we are now done and we move on to the intersection of three planes. The first case is case number 4. So this is where three planes intersect at exactly one point, and therefore your answer is not going to be a line, but rather a point in the intersection of all three planes. All right, so case number 4 is determining the specific point of intersection of three planes. So the equations that we're going to be dealing with are equation A, B, and C. And what you want to first do is check if any of the planes are parallel to one another. You want to make sure that none of them are parallel if you're dealing with a point of intersection on three planes. As you can see, normals 1, 2, and 3 don't have any scalar multiple that can make them all equal to one another. Therefore, they are not parallel to each other. Next, you want to do is determine whether it's coplanar or not. If it's not coplanar, you know you're dealing with a point of intersection on the three planes. So you do this by doing normal 1 dot normal 2 cross normal 3, and if it's equal to 0, it's coplanar, and if it's not, that means it's not. So I got -138 does not equal 0, so that means it's not coplanar, which means I'm dealing with a specific point on the three planes, and I gotta find that specific point. In order to find that specific point, what you first want to do is do the method of elimination. So I take equation A and equation B, and I do method of elimination to get 26y minus z equals -51. Now I want to cancel out the same variable between equation A and equation C. So then I get 46y minus 23z equals -61. I take my two resultant equations and put them together and do method of elimination again. Well, I can cancel out either y or cancel out z. I chose to cancel out z for simplicity reasons. And then I get 552y equals -1104. And then when you solve for y, you get y equals -2. Once you found out your y, you substitute this back into either one of your two resultants from your original method of elimination. I chose to do 46y minus 23z equals -69. When I subbed in the y equals -2 there, I got z equals -1. Now, once you figured out your y and your z, you sub both of these into one of your original questions in order to find your x. And I got x equals 3. And then given your x, y, and z, you are now given the point of intersection of all three of the planes, which is 3, -2, and -1. Now, having done cases 1, 2, 3, and just finishing 4, we've learned how to find the intersection of three planes at one point, but now we'll also learn the intersection of 3 points where there's an infinite amount of solutions, and your solution is actually going to be a line.
Next, we'll be looking at case 5, and this is when planes intersect in a line. When planes intersect in a line, there are an infinite number of solutions. The normals are also coplanar, but they're not parallel. So here we have a question: determine the line of intersection. And we have an example here. So the first plane is modeled by 7x plus y minus z equals 2. The second plane is modeled by 6x minus 2y plus 3z equals 1. And the third plane is modeled by 8x plus 4y minus 5z equals 4. The normal 1 equals 7, 1, -1. Normal 2 equals 6, -2, 3. Normal 3 equals 8, 4, and -5. Since none of them are scalar multiples of each other, we can determine that there are no parallels. So criteria 1 is met. Then we do cross product and then dot product of the three planes to determine if they're coplanar. So first we have dot product of or a cross product of plane 2 and 3, which ends up being -2, 54, and 40. And then we do dot product with plane 1, which is 7, 1, and -1, and we'll end up with -14 plus 54 minus 40 equals 0. And for 3 planes to be coplanar, it has to equal 0, which it does. Therefore, it's coplanar. Then we do elimination of 1 and 2. And first we'll be eliminating the x. So we'll end up with y in terms of z. And then we're going to be doing elimination of 1 and 3. So we cross out the y's. And we're going to have x in terms of z. Then what we can do is let z equal t. Therefore, z equals t, x equals 0.2 minus 0.05 t, y equals 0.25 plus 1.35 t. And basically what this does is makes it easier for us to plug in a value and get some numbers out since they're all in one variable. So what we have here is now the line of intersection, which is xyz equals 0.2, 0.25, 0 plus t bracket negative 0.05, 1.35, and 1. And that's how you find the line of intersection for 3 planes.
Now, having finished case number 5, we move on to case number 6. This is when all 3 planes are the exact same and lie on top of one another, and they are coincident, and there's an infinite amount of solutions because all the points are the same and all the lines are the exact same.
So now we'll be moving on to case 6, which are planes that are coincident and parallel. So in this example, we're going to determine if the planes are parallel and coincident. So looking at these 3 planes that are listed, the first thing we're going to do is find the normals for each plane. So the normals are 3, 6, -9 for plane 1. The normals are 1, 2, -3 for plane 2, and 2, 4, -6 for plane 3. So knowing these 3 normals, we can determine whether these are scalar multiples of each other. And we can see that normal number 2 for plane 2 is a scalar multiple if you multiply by 3, and you'll get the same normal for n1, which is for plane 1. And you can do the same for normal 2 to normal 3. As you can see, if you multiply normal 2 by 2, each point will reflect to the normal points in normal 3. Now, knowing that these are scalar multiples to each other will make you understand that these planes are parallel. So the second step now is to compare these planes in pairs to see whether or not they have an infinite amount of solutions. So the next step, we're going to do substitution and elimination. So the first part, we're going to take plane 1 and plane 2 and use substitution and elimination to determine if they have infinite solutions. So we're going to multiply plane 2 by 3, and then we're going to use elimination to cross out all the variables, and we're going to end up with 0 is equal to 0. Next, we're going to do planes 2 and 3. We're going to multiply plane 2 by 2, and then we're going to cross off the variables, as you can see over here, and we're going to end up again with 0 is equal to 0. Therefore, all planes are parallel and coincident, and there are an infinite amount of solutions because all planes are together.
Having finished case number 6, moving forward to case number 7 now. Case number 7 is when all three planes are parallel to one another, and at least 2 of them are distinct. So that means that there's a space in between at least 2 of them. So in this case, there are going to be no solutions, and all 3 planes are going to be parallel to one another.
Next, we'll be looking at case 7. This is when a system of planes is inconsistent and have no solutions. In this case, we're going to be looking at what happens when all the normals are parallel and at least 2 are distinct. This question, in a system, determine if 2 planes are parallel. So what we have here is plane 1 modeled by this equation, plane 2 modeled by this equation, and plane 3 modeled by this equation. Next, we're going to be analyzing the normals. So normal 1 is 6, 4, and 8. Normal 2 equals 3, 2, and 4, and normal 3 equals 9, 6, and 12. We can see that most of these normals are just scalar multiples of each other, and therefore we can determine that they are parallel due to them being scalar multiples. Next, we need to figure out if the planes coincide, and we do this by doing elimination. So we can take plane 1 and plane 2 and use elimination there. So what we end up with is 0 equals 1, and that cannot be true, therefore the planes do not coincide. Then we do elimination of 1 and 3 to figure out if the planes coincide there, and 0 equals 6.5, which is also not true, therefore they do not coincide. Then we can also do elimination of 2 and 3, and there we also have 0 equals 14, which is not true as well. Therefore the planes do not coincide. But since the planes are parallel, the normals are parallel, but the constants are not, we can determine that the planes are distinct.
Having learned case number 7, which is one of the inconsistent planes example, we're now moving on to example number 8. This is when two lines are parallel and the third one intersects both of them. In this case, there are also no solutions. So case number 8 is when there's two parallel planes and one plane intersects both at two different points. For when you're dealing with something like this, there are no solutions because you're going to have two lines of intersection rather than one line of intersection or infinite amount of points along a line of intersection. So the two equations that we're going to be dealing with are 3x plus 2y plus 4z equals 3, 6x plus 4y plus 8z equals 15, 2x plus 2y minus 2z equals 2. So the first thing you want to do is find the normals of them so you can classify what type of case you're dealing with. So normal 1, 2, and 3. As you can realize, normal 2 is the scalar multiple of normal 1 by a factor of 2. And normal 3 is not a multiple of either one of them. So you know that normal 1 and normal 2, so equations 1 and 2, are distinct parallel planes, which means that there is a gap in between them and they're not coincident, but they are both parallel to one another. And then you know that normal 3, since it's not parallel to them, it must intersect both planes at a point eventually, resulting in two different intersections, meaning that there are going to be no solutions to a question like this. Having finished case number 8, we now move on to the last case for the intersection of planes, which is case number 9. In this case, the planes intersect in pairs.
So now we'll be moving on to case 9, which are three planes that are intersecting in pairs of parallel lines. So now in case 9, all the normals are not parallel, therefore the planes are not parallel or coincident. So in the example, we're going to be looking at these three planes given here. So the first step is to first find all the normals and see if they're scalar multiples, and that will help us determine if the planes are parallel. In this case, they are not. Next, we're going to see if the planes are coplanar. And to do so, we're going to take the normals, and we're first going to do the dot product of n2 with first we're going to do the cross product of n2 with n3, then we're going to do the dot product of n1 with the cross product of n2 and n3. And the answer should be a 0, in which case this is a 0. Lastly, we're going to move on to proving if there are any solutions for this system of planes. So first we're going to do substitution elimination for two planes. So in this case we're going to do n1 and n2, and after doing substitution and elimination we're going to end up with negative y minus 8z is equal to negative 22. And then next we're going to take planes 1 and 3, do the same thing, but now we're going to end up with negative y minus 8z is equal to negative 56. Now taking those two together, we're going to do elimination and substitution again, and in this case we're going to subtract one from the other, and we're going to end up with 0 is equal to 34. This means that there are no solutions, and it proves that in a case 9 system of planes, there are three planes that intersect with one another with parallel lines, and none of them are parallel, and none of the intersections are coplanar.